Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to discuss about a very important distribution that is called as normal or Gaussian distribution. Now there is so much amazing things to probably learn about this particular distribution because most of the common data that exist in this world follows normal or Gaussian distribution. So let us go ahead and understand about this. And first of all, we'll go ahead with the definition. So here you can see that in probability theory and statistics, a normal distribution or Gaussian distribution is a type of continuous probability distribution for a real value random variable. So this is the first time I think you are hearing about continuous probability distribution. Till now, we saw about discrete probability distribution. So here, the most important point is that this kind of distribution is basically created for a continuous random variable. One of the most amazing feature of this specific distribution is that you'll be seeing this distribution wherein you'll be getting your data in the form of bell curve. So this is the kind of bell curve we will be getting. So all the Gaussian or normal distribution, if I consider x as a random variable, and let's say this x has some values of continuous random variable, this will follow a Gaussian or normal distribution. If this follows a Gaussian or normal distribution, then it usually follows a bell curve. Okay, and this is how your distribution will look like. Now, there are a lot of assumptions we can probably consider from this particular distribution, which is normal or Gaussian distribution. So over here, first of all, in this center region, here we basically have our mean value. So the mean will be equal to median, which will be equal to mode. So usually in a normal or Gaussian distribution, this is one of the property that we will be able to see. The mean of this particular distribution will be equal to the median. It will be equal to the mode. One more very important thing is that, let's say if x is a random variable which follows a normal or Gaussian distribution, this bell curve that we are specifically getting is a symmetric distribution. When we say symmetric distribution, that basically means 50% of the total values inside this random variable will be present in this side, and remaining 50% of the total distribution will be present in this side, right? Not only this, we'll still discuss many things about this normal or Gaussian distribution. So let's go ahead and let's talk about some of the notations that we are going to use. So one of the important notation that we use for a normal or Gaussian distribution, we say this is what we basically use for a normal or Gaussian distribution, n with some mean and variance value. Okay, so this is the notation that we specifically use. The next thing that you really need to understand are about the parameters. Now, what are the parameters that are used in normal or Gaussian distribution? One is mean. Mean belongs to a real value, which is nothing but mean over here. Then you have this variance. This variance also belongs to a real value and it is greater than 0. So which we specifically say it as variance. And this x that we are probably considering with respect to our data set or random variable, whatever values we have, this will also belong to a real value, right? Now, here you can see one of the diagram that we are specifically using. Now, since we are using continuous random variable, we know that the distribution that we specifically create is for a continuous random variable. So we are going to use something called as PDF, probability density function. Now, with respect to PDF, here you will be able to see with respect to different mean and variance value. So here you can see variance as it is increasing. You can actually see, like, let's say for the blue color, the variance is 0.2. The mean is 0, right? So 0 is the mean and variance is equal to 0.2. So here you are getting this kind of curve. When the variance increases to 1.0, you can see the spread of the data is also increasing. Similarly, when you see the variance is 5.0, still the variance is basically increasing, right? And in the case of variance of 0.5, you'll be able to see over here, this is my data. And here my mean is changing, okay? So in short, this basically indicates as the variance increases, right, the spread of the data also increases, right? One of the most common distribution of most of the data that you'll be able to see that it follows normal or Gaussian distribution. Some of the example that I would like to consider, let's consider the ages of, or let's say instead of writing ages, I will go ahead and write the weights of students in a class. Weights of students in a class. This may follow a normal or Gaussian distribution. The heights of students in a class. Right? This may follow a normal or Gaussian distribution. One of the most common data set that you will be looking as in the form of like if you're working as a data analyst or data scientist, one of the most common data set which is called as iris data set. So in this iris data set, you have 4 important features. One is petal length, then you have sepal length, right? Then you have petal width and sepal width. Petal width and sepal width. And based on these 4 features, we need to predict what flower it is. Usually this petal length usually follows a normal distribution. If we take values of different sample of flowers, and if you try to construct this with the help of PDF, it will be creating this normal distribution. But still the question comes, right? With respect to your random variable X, for any values, how this entire probability density function is created. So for this, for a Gaussian distribution or normal or Gaussian distribution, we use a PDF function, and this PDF function formula is given by 1 by sigma multiplied by root of 2 pi e to the power of minus half multiplied by x of I minus mu divided by sigma whole square. Okay, so this is the formula that we specifically use to calculate the PDF. When I say x of I, this is with respect to different data points. Okay, this is how the PDF is basically calculated. The probability of a number with respect to the random variable X, I'll be able to calculate it. Okay, and this is the formula that is used with respect to PDF. Okay, again, I will not go ahead and derive it because it will not be that important for you all to since we really need to understand about the distribution, so it won't be that important. So please, and do not even by heart this formula, because with the help of coding, if you see, we will be able to create this kind of distribution in a very easier way, right? We'll be using histogram, we'll be using kernel density estimator and all. Okay, so this is one of the important thing. Okay, now similarly, if we go ahead and see the mean of this distribution, the mean of normal or Gaussian distribution. So in order to get this, the formula is very simple, and we have already discussed about is mean is equal to summation of I is equal to 1 to n, x of I divided by n, right? So this is the mean formula that we specifically use. Then let's go ahead and understand about the variance. Now in order to compute the variance, it is nothing but sigma square. And here again, we'll go ahead and write I is equal to 1 to n, x of I minus mean whole square divided by n, right? So this is the formula for the variance. And finally, for the standard deviation, it is nothing but square root of variance. So this is what we basically discussed in the initial time, right? So these are the important properties that we can actually see with respect to a normal or Gaussian distribution. Okay. And here you can actually see that if we compare with respect to the probability density function and cumulative distribution function, for any probability density function, right, with respect to a continuous random variable, you'll be able to see that we'll be getting this kind of S curve. And I've already spoken about probability density function, talking about the area under the curve, right? So that entire information I've given it in the initial sessions. Okay. Now let's go ahead and talk about one very important thing. See, the reason we are understanding about all this distribution, because from this distribution, we can make some basic and some meaningful assumptions. Now, one of the important assumptions about Gaussian or normal distribution, we basically say this as empirical rule. So let me just go ahead and talk about empirical rule of normal or Gaussian distribution. Okay. Empirical rule of normal or Gaussian distribution. Now, what is this specific empirical rule? And just by seeing this particular graph, you will definitely be able to understand. Okay. And this rule is basically called as 68, 95 and 99.7% rule. Okay. And here it basically says mu is over here. Mu plus 1 standard deviation to the right, mu plus minus 1 standard deviation to the right, left, mu plus 2 standard deviation to the right, mu with 2 standard deviation to the left, mu plus 3 standard deviation to the right, and mu minus 3 standard deviation to the left. Let's say I have a random variable, and in this particular random variable, I have around 50 data points, let's consider. And we are considering, let's say that this follows a normal or Gaussian distribution. Let's say that. When we say that this follows a normal or Gaussian distribution, that basically means that, and how do we say that this follows a normal or Gaussian distribution? That we'll be seeing in the upcoming video. We specifically use something called as QQ plot. And with the help of QQ plot, we'll be able to determine whether a random variable X will follow a normal or Gaussian distribution. Okay, that we'll discuss about it. Don't worry. So if we consider a random variable and if we say that, hey, if it is following a normal or Gaussian distribution, so there is some empirical rule that we can basically derive from it. And it is already derived. And these are the assumptions we can probably take. Okay. And these assumptions are related to probability. Okay. So these are something related to probability. So let's go ahead and discuss about this. So here I will just go ahead and write probability of mu minus sigma. Okay. Mu minus sigma basically means, let me just go ahead and write first of all, mu minus sigma less than or equal to a random variable less than or equal to mu plus sigma. Okay. Now what does this basically mean? This basically means a probability of a random variable, of this random variable, any random variable, to be between mu minus sigma to mu plus sigma, that is within the first standard deviation with respect to your mean, right? First standard deviation to the right, first standard deviation to the left. So within this first standard deviation, I'm just saying that, hey, what is the probability of a random variable to be between the first standard deviation? This is approximately equal to 68%. Okay. Similarly, if I go ahead and write, this is what this rule specifies, 68, 95, 99.7. Similarly, if I go ahead and say the probability of a random variable to be present between two standard deviation, right? Within this region, what is the probability? It is approximately equal to 95%. Similarly, the probability of a random variable to exist between 3 standard deviation, within the region of 3 standard deviation, this is approximately equal to 99.7%, right? So these are basically talking about the probability of a random variable to exist between first standard deviation, second standard deviation, and third standard deviation. I can also mention that, let's say if I have this random variable, let's say in this there are 50 numbers and it follows a good normal or Gaussian distribution. Within the first standard deviation, 68% of the distribution will fall within the first standard deviation. Similarly, 95% of this distribution, 95% of this particular values or data points will fall within 2 standard deviation region. Similarly, 99.7% of this entire distribution will fall between this 3 standard deviation, right? Within the area between 3 standard deviation. And that is what is the empirical rule, right, of this normal or Gaussian distribution. Okay. So I've already spoken about all the examples. Most of the data points, probably if you will be seeing this kind of distribution follows a lot of data points, right? And I'm not saying this, okay? I'm not saying the weights of a student in a class will follow normal distribution. This is already proven. Proven by whom? By doctors, okay? So doctors collected a lot of data for students with respect to weights, right? Similarly, this was basically done by doctors. I'm just taking an example. Similarly, in the case of iris dataset, who collected this data? Researchers, when they were building the models, right? So most of the data points that exist in this entire universe, okay, actually follows a normal or Gaussian distribution, okay? Not every, but yes, most of them. So this was mostly about the empirical rule. We also saw that this empirical rule is very important just to understand that how much distribution is falling in which standard deviation and all, within the region of which standard deviation, right? So I hope you were able to understand about this normal or Gaussian distribution. This was it from my side. I will see you all in the next video where we'll be discussing about more other types of distribution. So yes, this was it. I'll see you all in the next video. Thank you.